chances of this happening are 1 over I factorial, right? Because there are I factorial of possible outcomes and I factorial square of, sorry, I factorial square possible outcomes, and only I factorial of them are favorable, namely when the first I are the same as the last one. And then, you know, take the union, the event that the permutation is overlapping is the union of all these events from 2 to n minus 2. The union is bounded from above by the sum, and the sum is bounded from above by the infinite sum, which is, of course, e minus 2, which marks the first time in my life that e minus 2 is the unit sum. So the number of overlapping permutations is about 0.71. So the number of non-overlapping ones is at least 0.28. So already we have done almost nothing, and nevertheless we see that a relatively big fraction of permutations is non-overlapping, so the Ellis-Alden-Lloyd conjecture is solved for them. So then what if we try to do something more serious? So let A n be the probability that the random permutation of length n is non-overlapping. Here are the first few values. And then, for interestingly, or maybe not so interestingly, but certainly painfully, the sequence A n behaves differently for even numbers and odd numbers. For even n, there is this relatively simple recurrence because, well, the probability of permutation being non-overlapping is 1 minus the probability of overlapping. If it is overlapping, then probability for that is counted by those numbers, which is again straightforward. Yeah, it's based on a simple observation that which I have already said. Now, if n is odd, then the situation is more complicated, and it's one that I can't completely handle. And there's a nice question, or maybe 2 nice questions given there. So what's different is that it could be a case that the permutation of length 2k plus 1 is overlapping because the first k plus 1 entries can overlap with the last k plus 1 entries, but only that. Nothing else can happen. So the smallest index I, so that the first I entries form an isomorphic pattern to the last I entries, is k plus 1. Here is an example. See, in this one, the first 3 patterns form a 1, 3, 2 pattern. The first 3 entries form a 1, 3, 2 pattern. And so do the last 3. But it doesn't work for the first 2. So let Bn be the number of the probability that if you select a random permutation of length n, the n is odd, then the permutation is like that, which I call almost non-overlapping. So it's overlapping, but with only one index, and the index has to be k plus 1 if n is equal to 2. So we have this recurrence, which is different for odd n and even n. And because in the odd case, there is that annoying error term with Bn. So I have a few questions here. First, what can be said about Bn? So it's not terribly difficult to prove that it's not more than an minus 1, so the previous big probability, the previous probability that a random permutation of length n minus 1 is non-overlapping, that divided by n. At the beginning, this is remarkably good. So that for n equals 3 and n equals 5, actually equality holds. After that, it gets progressively worse. So one question would be, what can be said about Bn? And it's surprisingly difficult. One other thing that I would like to know is, yeah. So look at this form. So I would like to rigorously prove that the sequence an is monotone decreasing. So the longer the permutation, the less is the chance that it is non-overlapping, which is, intuitively should be obvious because the longer the permutation is, the more chance it has to overlap with itself, because the more chances you have to find an I, so that the first I and the last I are the same. Now, it's trivial that an decreases as you go from an even number to an odd number, because for even numbers, the formula, for even numbers, the formula is this. So like if n is 6, then you have this formula. And if you go from n6 to n7, then there will be the same thing minus the Pn, which is positive, so you subtract the number and that's it. However, when you go from odd to even, then it's not obvious. Then what you have to know is that, what you want to know is that there are the following two events, and one of them is more likely than the other. So one of them is the following. I will say concrete numbers. That you choose a random permutation of length 7, and that the pattern of its first 4 entries is the same as the pattern of its last 4 entries, right? They intersect in the middle. And there is no smaller I, so that this would happen. So this is one event. The other event is that now you have you look at all permutations of length 8. You pick one at random. And then the pattern of the first 4 entries is the same as the pattern of the last 4 entries. So you would think that the second one is more likely, and it probably is, but it's not obvious how to prove it. For one reason for that is that in the first case, when I looked at permutations of length 7, then I had really more conditions than just that the first 4 and the last 4 are the same. Because I also said that, and there is no smaller index, so that would happen. And so that makes your underlying set of permutations rather complicated. So then, of course, the other question, and what was the motivation of the whole thing, is what can you say about AN? And so here, the thing is that you can make a probably difficult theoretical arguments which limit AN better, but barely better than what you can get by quite crude estimates, because those factorials in the denominator make the summons decrease very fast. So even if you get just the first few numbers right, after that, your estimate will not improve by very much, even if you do more work. So the motivation there is kind of not upward. But anyway, what I get is that just by computing the first 7 correct values and then saying that the error term after that is absolutely minuscule, I get this, that it's about 0.3641, and then Maple computes you the first 200 numbers, and there are basically no changes in that. So more than 1/3 of the permutations are non-overlapping, and modulo Bona and Remmel writing up will prove more than 1/3 of the Elizalde-Noy conjecture. So, thank you.
Any questions?
Okay, the natural extension would be these two overlaps. They only have at most one overlap.
Right. But you count how many such permutations are there. I don't know. You would think that would be harder, for example, so I can't even handle one.
Okay, let's thank the speaker again.